Come in, come in, come in. I introduced some basic notions on functions in my last class. Is there anything that needs to be revisited on that front? Are you all comfortable with everything that I discussed in my last class on basic functions? Towards the end of my last session, I introduced a function which I said we'll encounter very rampantly. That's the modulus function, right? Some basics of modulus function was introduced to you. In line with that, let me get you to terms with yet another very basic function, which would be almost like bread and butter in all of calculus that we're going to deal with. And that function is the greatest integer function. The function is designated as y equal to f of x, box of x, which is the greatest integer less than or equal to x. In simple terms, what it really means is, if x is any real number, then there are two possibilities for that real number. That real number could be an integer, or that real number may not be an integer. Either it's an integer or it's not an integer, right? Now, whenever x is an integer, then box of x is synonymous with x. X and box x coincide on the real number line. For example, if x is 2, then box x will also be 2. When x is an integer, x and box x are the same. When x is minus 1, box of x is going to be minus 1. When x is 0, box of x is going to be 0. So whenever x is an integer, box of x is the same as x. Now, when x is not an integer, obviously it would be sandwiched between two integers. It would lie between two integers, right? If x is not an integer, it's certainly going to lie between two integers. That means x would lie between two integers I and I plus 1. When x is not an integer, it must lie between two integers. Now, when x lies between two integers, then the integer to the immediate left of x is called box x. What is the integer to the immediate left of x? I in this case. The integer to the immediate left of x is I. So in this case, box of x is I in this case. The integer to the immediate left of x on the real number line is box of x when x is not an integer. And whenever x is an integer, box of x is synonymous with x. Clear? Which means Say x is 3.7. X is 3.7. Now it's surrounded on two sides by two integers. X is 3 and there is an integer equal to 4. This is I and this is I plus 1. Then what would box of x be? Box of x would be 3. The integer to the immediate left of x is 3. The integer to the immediate left of x is 3. So box of x will be 3 by 4. Oh, left right का problem आ गया. Go home today and practice left, right, boom. Alright? If there is a problem of left and right in your case, go back home for 1 full week. Do nothing but practice left, right, boom. Alright? So the integer to the immediate left of x is 3 in this case. So box of x will be 3. Clear? And when I said it's the greatest integer less than or equal to x. So when x is not an integer, what are the integers to the immediate left of, what are the integers? All the integers to the left of 3.7. 3, 2, 1, 0, minus 1, minus 2, etc. Right? These are the integers to the left of x. And of these integers to the left of x, which is the largest? 3. That's what. So greatest integer less than or equal to x. Of all the integers to the left of x, choose the one which is the greatest. Which is the greatest. So of all the integers to the left of x, when x is not an integer, the greatest is 3. That's another. That's why it's called the greatest integer less than or equal to x. Equal to x means when x is an integer, box of x will be equal to x. That's what it means. Right? So, say when x is minus 3.7, then minus 4 and minus 3. These are the two surrounding integers. Then what would box x be? Minus 4. Box of x would be minus 4. Yes or no? Are you there with me? Right? So, one way or the other, the output of box of x will always be an integer, no matter what x is. The output of box of x will always be an integer. I mean, when x is an integer, box of x is x. When x is not an integer, then box of x is the integer to the immediate left of x. So, in either case, the output of box of x will always be an integer. Like I told you, the output of mod of x will never be a negative number, will be a number greater than or equal to 0. The output of box of x will always be an integer, So, if somebody said, box of x is 1.2, what is x? Go to hell, nothing. Right? You can't find an x whose box is 1.2, right? But when somebody said, box of x is 1, what would x be? Not just one value. X can lie anywhere from 1 to 2. If box of x is 1, then x could be anywhere, x could be 1 for sure, and x could be any value from 1 to 2 to the exclusion of 2. If x is any number from 1 to 2, then its box would be 1. When x is equal to 2, then box will be 2. So, when x is greater than or equal to 1 but less than 2, box of x is 1. So, if somebody said box of x is 1, what is x? Then you can claim that x is greater than or equal to 1 but less than. Because when x is equal to 2, then box of x will become equal to 2. Then it will no longer be 1, right? That's why in this description, if I want box of x to be equal to 1, then x cannot be equal to 2. Because if x were to be equal to 2, box of x will become 2. However, you can make x as close to 2 as you like, and box of x will still be 1, right? So, In general, if I said box of x is I, if I said box of x is I, any integer, then I can claim that x can be greater than or equal to I, but less than I plus 1. If box of x is I, very clearly, I and I plus 1. If box of x is I, this is box of x. Realize that x can be any value between I and I plus 1. Then box of x will be I. Yes or no? So box of x equal to I means x greater than or equal to I, but less than I plus 1. Clear? If I said box of x greater than 2, if I said box of x greater than 2, that means box of x could be 3, 4, 5. These are permissible values of box of x. The output will always be an integer, right? So box of x greater than 2, that means the permissible values of box of x can be 3, 4, 5, etc. Right? These would be the permissible values of box of x. Now, this is the real number line, etc. Now, box of x would be 3 when x lies anywhere from 3 to 4. Box of x would be 4 when x lies anywhere from 4 to 5. Box and so on and so forth. Right? That means, whenever I say box of x greater than 2, x would be greater than or equal to 3. X would be greater than or equal to 3. Yes or no? Box of x greater than 2 would mean x would be greater than or equal to 3. X could be 3. X could be 3 plus. Anywhere to the right of 3 or including 3, box of that number would be greater than 2 for sure. Clear? So in general, if I said box of x is greater than I, box of x is greater than I, can I not conclude that x must be greater than or equal to I plus 1? X must be greater than or equal to I plus 1. Clear? Are you there with me? Right? Now, if box of x is less than 2, for example, then what are permissible values of box of x? Box of x can be 1, 0, minus 1, minus 2. These are permissible values of box of x, right? So box of x less than 2 means box of x could be 1. When would box of x be 1? When x is greater than or equal to 1 but less than 2. Yes or no? When x is greater than or equal to 1 but less than 2, then box of x would be 1. When x is greater than or equal to 0 but less than 1, then box of x will be 0. When x is greater than or equal to minus 1 but less than 0, box of x would be minus 1. So then, whenever I say box of x less than 2, then can I not say that x must be less than 2? X less than 2. For example, if x lies here, box of x would be 1. When x lies here, box of x would be 0. When x lies here, box of x would be minus 1 and so on. But x can't be equal to 2. Because if x were to be equal to 2, if x were to be equal to 2, then box of x will be equal to 2. So, box of x less than 2 means x less than 2. X less than 2. So, in general, if I said box of x less than I, then I can claim that x must be less than I. X must be less than I. That could be claimed. Yes or no? Now, very clearly, when x is greater than or equal to, when x is greater than or equal to 0 but less than 1, what is box of x? 0. When x is greater than anywhere from 0 to 1 to the inclusion of 0 but to the exclusion of 1, then box of x will be 0. Because for all these points, the integer to the immediate left of x would be 0. Right? When x is greater than or equal to 1 but less than 2, what would box of x be? 1. When x is greater than or equal to 2 but less than 3, what would box of x be? 2. When x is greater than or equal to 3, less than 4, what would box of x be? 3. And so on and so forth. Right? Now, when x is greater than or equal to minus 1 but less than 0, what would box of x be? Minus 1. Right? For any number lying between minus 1 and 0, the box of that number would be minus 1 because the integer to the immediate left of x would be minus 1. This is going to be minus 1. About it? Right? When x is greater than or equal to minus 2, less than minus 1, what would box of x be? Minus 2, and so on and so forth. Yeah. So this is like the description of box of x in various integers, Evidently then, the graphical look of this, y equal to fx equal to box of x. When x is greater than or equal to 0 but less than 1, which includes 0 but excludes 1 in this description. Box of x is 0, y is 0 for this description. So including 0 but excluding 1. So in this description, when x is greater than or equal to 0 but less than 1, box of x is 0. Right? At x equal to 1, box of x jumps to 1. When x is equal to 1, box of x jumps to a value equal to 1, right? And then for x greater than or equal to 1 but less than 2, box of x will be 1. For x greater than or equal to 1 but less than 2, box of x will remain 1. But it excludes the description x equal to 2. So 2 is not included in this description. Why? Because at x equal to 2, there is an abruptness. At x equal to 2, box of x becomes equal to 2. At x equal to 2, box of x becomes equal to 2. And then from x equal to 2 to x equal to 3, box of x remains 2. Again in this description, 2 is included but 3 is excluded. So in any of these intervals, realize that the left end of the interval is included in the description, whereas the right end of the interval is excluded from that description. The left end of the interval is included, whereas the right end of the interval is excluded from that description. And so on and so forth. We get this from 3 to 4. And so on and so forth. Now, to the left of x equal to 0. When x lies between minus 1 and 0, that means when x is greater than or equal to minus 1 and less than 0, box of x would evidently be minus 1, right? For any x lying between minus 1 and 0, which includes minus 1 but excludes 0, box of x will be minus 1. So why is minus 1 in this description? And in this description again, the right end is excluded, the left end is included. Then from minus 2 to minus 1, x greater than or equal to minus 2 but less than minus 1, box of x would be minus 2. It includes minus 2 but excludes minus 1 and so on and so forth. This is the graphical description of y equal to box of x. Right? You can see that This description changes behavior at certain points. What are the points where it changes behavior? For example, when it's going from 0 to 1, 0 to 2, for example, it's changing behavior at x equal to 1. At x equal to 1, it exhibits an abruptness. At x equal to 1, the function exhibits an abruptness. It suddenly jumps to 1. There is a sudden jump to y equal to 1. This point is a kink. This point is a kink, not included in the graph, whereas this is included in the graph. Again, from 1 to 2, it's going fine. And x equal to 2, again, it demonstrates an abruptness. It jumps equal to 2 and then exhibits a uniform behavior. And then at x equal to 3, it exhibits an abruptness and so on and so forth. So what's really transpiring here is, each time x is an integer, the quantity inside the box, each time the quantity inside the box is an integer, there is an abruptness in the behavior. There is abruptness in the behavior. There is change of character. There is change of character of the function, right? See, from 0 it jumps to 1. From 1 it jumps to 2. And when does that happen? The transition occurs whenever x is, the quantity inside the box is an integer and abruptness is observed. A change of character, a change of behavior is observed in the function. Clear? So whenever the quantity inside the box becomes an integer, then for that value of x, whenever the quantity inside the box becomes an integer, then for that value of x, there is change of behavior, there is change of character. Clear? Now, suppose I have a function y equal to fx equal to box of x squared. Suppose the domain of this function I give as x greater than or equal to 0 is the domain of the function, right? Suppose I define this function y equal to box of x squared for x greater than or equal to 0. Now, whenever the quantity inside lies between 0 and 1, whenever this number lies between 0 and 1, then the box of this number will be 0. Box of this number would be 0. Whenever the quantity inside the box lies between 0 and 1, then the box of that number is going to be 0. So then, this box of x squared, whenever x squared is greater than or equal to 0, less than 1, box of x squared would be 0. Box of x squared would be 0. Right? Whenever x squared is greater than or equal to 1 but less than 2, whenever the quantity inside is greater than or equal to 1 but less than 2, box of that quantity would be 1, right? Be 1. Whenever the quantity inside the box is greater than or equal to 2 but less than 3, box of that quantity would be 2. X squared greater than or equal to 3 but less than 4, box of x squared would be 3, and so on and so forth, right? That's what we learned. Now, whenever x squared is greater than or equal to 0 and less than 1, and x is a positive greater than or equal to 0, can I say that x must be greater than or equal to 0 but less than 1? X must be greater than or equal to 0 but less than 1. This implies x greater than or equal to 0 but less than 1, right? This will reduce to corresponding x greater than or equal to 0 but less than 1, right? Now, what would this reduce to? X squared greater than or equal to 1 but less than 2 would reduce to x greater than or equal to 1 but less than root 2. Whenever x squared is greater than or equal to 2, less than 3, x would be greater than or equal to root 2 but less than root 3. Whenever x squared is greater than or equal to 3, less than 4, x must be greater than or equal to root 3 but less than 2. And so on and so forth. Yes or no? Now, if I have to draw y equal to fx versus x, and the domain of this function I have already said is x greater than or equal to 0 is the domain of definition of this function. Y equal to fx equal to box of x square. Now when x is greater than or equal to 0 but less than 1, box of x squared would be 0. Zero included in this interval of description, but 1 excluded from this description, right? Whenever x is greater than or equal to 1 but less than root 2. That means from 1 to root 2, from 1 to root 2 that includes 1 but excludes root 2. Box of x squared would be 1. So including 1 and excluding root 2, box of x squared would be 1. 1 is included in that description whereas root 2 is excluded. Again, for x greater than or equal to root 2 less than root 3, which includes root 2 but excludes root 3. The left end is included, the right end is excluded from the description. Box of x squared is 2. And so on and so forth, and so on and so forth, etc. Right? Now, observe. So this is the graph of y equal to box of x squared versus x. Right? This is the graph of y equal to box of x squared versus x. Observe keenly that this graph exhibits change of character, change of behavior at 1, root 2, root 3 and so on and so forth. These are the points where there is change of character. And do you realize that at x equal to 1, the quantity inside is an integer. At x equal to root 2, the quantity inside the box is an integer. X squared is an integer. At x equal to root 3, the quantity inside is 3, which is an integer. Similarly, at x equal to root 4, the quantity inside will be an integer and so on and so forth. So the change of behavior in box of a function, in box of the function is x squared here. The quantity inside is x squared. There is change of behavior each time the quantity inside becomes an integer. See, x square becomes an integer at x equal to 1, x square becomes an integer at x equal to root 2, at x equal to root 3, at x equal to root 4, at x equal to root 5, right? In general, at x equal to root I. In general, at x equal to root I, x square will be an integer. Yes or no? Right? So at these points, at x equal to root I, this function exhibits change of character, change of behavior. Right? I hope all of you are fine with this. Huh? Suppose now, I want to draw the graph of y equal to fx, which is box of sin x. In the interval, the domain, let's say, is x greater than or equal to 0, less than 2 pi. X greater than or equal to 0, less than 2 pi. I want to draw the graph of y equal to fx, which is box of sin x for x greater than or equal to 0 but less than 2 pi. Now, first of all, observe the graph of y equal to sin x alone. Just observe the graph of y equal to sin, for instance. In the interval 0 to 2 pi, 0 pi, 2 pi. This is the graph of y equal to sin x versus x in the interval 0 to 2 pi, right? Now, at x equal to pi by 2, sin x becomes equal to 1, right? At x equal to pi by 2, sin x becomes equal to 1. At x equal to pi, sin x becomes equal to 0. At x equal to 3 pi by 2, sin x becomes equal to minus 1. At x equal to 2 pi, sin x becomes equal to 0. Yes or no? Right? Now, let me map it onto the graph of y equal to box of sin x. Now, what you must designate as the nodes. Nodes are the points which henceforth I would refer to as those at which there is a change of behavior exhibited. Change of character exhibited. So in this case, like I said, each time the quantity inside sin x, that is, becomes an integer, at that point there would be an observable change of behavior. Okay. At what points between 0 and 2 pi is there a change of character that you would observe? At x equal to pi by 2? Because at x equal to pi by 2, sin x becomes an integer. At x equal to pi, it becomes 0. At x equal to 3 pi by 2, it becomes minus 1, right? So you're going to delineate the nodes across the x-axis. The nodes are now 0, there is pi by 2, there is pi, and there is 3 pi by 2, and there is 2 pi. Right? Hey, notice that when x is greater than or equal to 0 but less than pi by 2, see? When x is greater than or equal to 0 but less than pi by 2, sin x lies between 0 and 1. Sin x lies between 0 and 1. So box of sin x will be 0, right? Box of sin x will be 0. Yes or no? Whenever x lies between 0 and pi by 2, to the inclusion of 0 but to the exclusion of pi by 2, sin x lies between 0 and 1. So box of sin x is going to be 0. Box of sin x is going to be 0. So when x is greater than or equal to 0 but less than pi by 2, box of sin x is going to be 0. Why? Because sin x lies between 0 and 1. So box of a number lying between 0 and 1 is going to be 0. Right? At x equal to pi by 2, sin x becomes equal to 1. So box of sin x will be 1. At x equal to pi by 2, box of sin x will be 1. So at x equal to pi by 2, box of sin x becomes equal to 1. Box of sin x becomes equal to 1. Yes or no? Now, for x greater than pi by 2 but less than pi, sin x for x greater than or equal to pi by 2 but less than pi, sin x lies between 1 and 0. Sin x lies between 1 to 0. So then what would box of sin x be? 0. See again, this is a number lying between 0 and 1. Right? For at x equal to pi by 2, exclude that. For x greater than pi by 2, for x greater than pi by 2 but less than pi, what would sin x be? Sin x would be a number lying between 0 and 1. So what would box of sin x be? 0. Box of sin x would be 0. Box of sin x would be 0. Yes or no? See, for any x lying between pi by 2 to pi, sin x lies between 0 and 1. So box of sin x would be 0. Yes or no? If sin x lies between 0 and 1, box of sin x is going to be 0. Alright. So for x greater than pi by 2 but less than pi, again sin x is 0. Sin x is 0. At x equal to pi, sin pi is 0. At x equal to pi, sin pi, which is 0, so box of 0 is going to be 0. So at x equal to pi is going to be 0. So this point is included in that description. Yes or no? Confused? Yes, Karishma. See, when x lies between 0 and pi by 2, sin x lies between 0 and 1. So box of sin x is going to be 0. Right? At x equal to pi by 2, sin x becomes equal to 1. So box of sin x will be 1. For x greater than pi by 2 and less than pi, sin x lies between 0 and 1. So box of sin x will be 0. So for x greater than pi by 2 and less than pi, box of sin x is 0. At x equal to pi, sin pi 0. So box of sin pi is 0. So at x equal to pi, box of sin pi is going to be 0. Now, for x greater than pi and less than 3 pi by 2, for x greater than pi but less than 3 pi by 2. For x greater than pi but less than 3 pi by 2, do you realize that sin x lies between 0 and minus 1? For x greater than pi but less than 3 pi by 2, sin x lies between 0 and minus 1. And then box of sin x would be minus 1. Box of sin x would be minus 1. If sin x lies between minus 1 and 0, box of sin x is going to be minus 1. So for x greater than pi but less than 3 pi by 2, it does not include pi because at x equal to pi, it's 0. Whereas when x is just slightly greater than pi, sin x lies between 0 and minus 1. So box of sin x is going to be minus 1. Box of sin x is going to be minus 1. So then it takes over this. At x equal to 3 pi by 2, sin x is minus 1. So box of sin x is going to be minus 1. At x equal to 3 pi by 2, sin x is minus 1. So box of sin x is going to be minus 1. So this point is included in this description. Clear? And then 3 pi by 2 to 2 pi. Again, in the interval 3 pi by 2 to 2 pi, x greater than 3 pi by 2, less than 2 pi. Realize that sin x lies between minus 1 and 0. So box of sin x is going to be minus 1. See? No? When x is greater than 3 pi by 2 but less than 2 pi, sin x lies between minus 1 to 0. So box of sin x would be minus 1. So 3 pi by 2 to 2 pi minus 1, minus 1. However, at x equal to 2 pi, sin x becomes 0. So box of sin x will be 0. Clear? At x equal to 2 pi, box of sin x is going to be 0. So this is the graph of y equal to box of sin x versus x. Box of sin x versus x. Clear? Now, one thing that you might counter me with is at x equal to 3 pi by 2, it's an integer equal to minus 1. Yet at x equal to 3 pi by 2, there is no change of character. The line continues with the same trend. So what I actually meant was when I said that whenever the quantity inside is an integer, then that value of x needs to be explored. You must keep it as a node on the real number line for further investigation. That point is likely to be one where a change of behavior is offered. That could be one of the possibilities where a change of behavior may be observed. Right? Can I wrap this off? This is understood by all. Right? Did you get me right on this? And now, let me look at some basic properties of this box function or the greatest integer function. One thing, this is x, then the integer to the immediate left of x is designated as box x. This is going to be I plus 1. This is going to be I plus 1. Right? Going to be I minus 1. Now, this length is equal to 1 unit. Between I and I plus 1, the length on the real number line is 1 unit. So, this is less than 1 unit. This is less than 1 unit. Now, so this is where x is located. Now, x minus 1 would be 1 unit behind x. X minus 1 would be 1 unit behind x. And this is less than 1. This is less than 1. So, would you not believe that x minus 1 will be located somewhere here to the left of I? Right? If x is here, this is less than 1 unit. So, x minus 1 would be located to the left of box x. Right? And x could jolly well coincide with box x. X could jolly well coincide with box x. Now, an important inequality that we arrive at based on this foundation is that box of x, first of all, will always be greater than x minus 1. Box of x will always be greater than x minus 1 because it's to the right of x minus 1, right? But can be equal to x or will be less than x. Either, see, if x is an integer, box x could coincide with x. So, box x could become equal to x. Else, if box x is not equal to x, box x must be to the left of x. Either box x will be equal to x or box x will be to the left of x. That means either less than x or equal to x. So, then this is quite a useful inequality. Box x greater than x minus 1, less than or equal to x for any real x, right? You know that this all. Now, suppose this is x and the two surrounding integers are I and I plus 1. I and I plus 1. I is box of x. I is box of x. Right? I is box of x. Now, the distance between I and x, the distance between I, which is box x, and x, is called the fractional part f of x. The distance between I and x is called the fractional part of x. F is the fractional part of x. Which is distance between x and box x. Distance between x and box x, that's the fractional part of x. Now, if x coincided with I, that means if x was an integer, then this f would have become 0. Distance between x and box of x would be 0 if x is an integer, right? So, if x is an integer, then the fractional part of x is 0. Obviously, fractional part of x would be 0. Because the distance between x and box x on the real number line is 0. If x is not an integer, x greater than I, less than I plus 1, if x is not an integer, then that means if x starts from I to the right of I and falls slightly short of I plus 1, then the fractional part of x will grow from 0 and can be brought as close to 1 as you like, but the fractional part of x will never be equal to 1. Why? The moment x coincides with x plus 1, then fractional part of it will become 0. Fractional part of it will become 0. When x is equal to I, then the fractional part will become 0. When x is any other number lying between I and I plus 1, the fractional part will be greater than 0 but less than 1. Realize that? Fractional part will never become equal to 1. This is the fractional part. You might be tempted to believe that what if x coincides with I plus 1? Then this length becomes 1 unit. But then if this length, when x coincides with I plus 1, x is an integer and its fractional part will be reduced to 0. Right? Yes or no? So then the fractional part of x will always be a number. The fractional part of x will always be a number which will be greater than or equal to 0 but less than 1. It will never be equal to 1. I hope you realize it can be 0. When x coincides with an integer, the fractional part of x can indeed be 0. When x becomes I plus 1, then also fractional part is 0. When x is any number lying between I and I plus 1, the fractional part of x is greater than 0 but less than 1. The fractional part of a number can be brought as close to 1 as you like, but will never become equal to 1. Because if x can be made very, very close to I plus 1, but still to the left of I plus 1, then the fractional part of x is still like very close to 1, but will never become equal to 1. The moment you choose to degenerate x with I plus 1, then the fractional part of x will become 0. Yes or no? So as x goes from I to I plus 1, what's happening to the fractional part? The fractional part is increasing from 0. It's becoming like 0.1, 0.3, 0.8, 0.9, 0.99, 0.999, 0.999999, etc. But it's not like it will ever become equal to 1. Right? Okay. So now this is important, and the fractional part of a number is just the distance between the number and its integer part. This is its box x is also called the integer part of the number, right? So f, the fractional part of a number, any real number, is like the distance between x and box x. It's the distance between x and box x, right? No, because this will never be a negative number. X can never be to the left of box x. So this will never be a negative number. So why take its modulus? X can never be to the left of box x. You realize that? So x can never be less than box x. X can be at best equal to box x or will be greater than box x. So this will always be a number greater than 0 or equal to 0. But it will never be negative. You still confused? No. So x minus box x is always greater than or equal to 0. You don't have to take its modulus. It will be unnecessary, right? And it's commonly designated within curly braces as fractional part of x, like this. This means fractional part of x. X minus box x, that's fractional part of x. So this is the integer part, this is the fractional part. So any number x can be written as I, its integer part, which is box of x, plus f, which is its fractional part. Any number x, the real number x, can be written as I plus f, where I is an integer and f is a non-negative number lying between 0 and 1. Non-negative number lying between 0 and 1. F cannot be equal to 1. F can be brought as close to 1 as you like, but will never be equal to 1. But can be equal to 0. When will it be equal to 0? When x is an integer, its fractional part will be 0. Right? No, I said f is equal to 0 when x is equal to y. When x is an integer, I said f is equal to 0. That's what I said. No, then obviously f is not 0, because if x is any number lying between I and I plus 1, then f is not 0. But if I combine these two, that means when I say x greater than or equal to I less than I plus 1, then f is greater than or equal to 0 but less than 1. This is a general remark about the fractional part. It could be equal to 0, or it would be any number lying between 0 and 1 cannot ever be equal to 1. The fractional part cannot be equal to 1 ever. Clear? Yeah, feel free to ask if there are more questions. So far so good, right? Now, the fractional part of x. The fractional part of x is a function of x, and it's going to be the number minus its integer part. The number minus its integer part, that's the fractional part of x. That's the fractional part of x. Yes or no? And the graph of this function will always lie between y equal to 0 to y equal to 1. It could be equal to 0 but never equal to 1. So y, for any value of x, y will always be greater than or equal to 0 but less than 1. The output of these curly braces will always be a number lying between 0 and 1. Could be 0 but never will be equal to 1. That's the output of this number. So one thing, if I have to draw the graph of y equal to fractional part of x versus x, then I know for sure that y must be greater than or equal to 0 but less than 1. Y must be greater than or equal to 0 but less than 1. This is y equal to 1. So the graph of this is confined between y equal to 0 and y equal to 1. It's confined between y equal to 0 and y equal to 1. It will not transcend these two barriers. Right? Huh? No. Now, y equal to fractional part of x, which is x minus box x. Now, when x is greater than or equal to 0, less than 1, what would box x be? 0. So, y equal to fractional part of x will be equal to x. Whenever x itself is a number greater than or equal to 0, less than 1, then its fractional part will coincide with the number itself. Fractional part of x is x minus box x. And when x is greater than or equal to 0 but less than 1, box of x is 0. Right? So, fractional part of x will be simply x when x is greater than or equal to 0 but less than 1. Now, when x is greater than or equal to 1 but less than 2, what would box x be? 1. Box of x would be 1. So, fractional part of x would be x minus 1. Right? When x is greater than or equal to 2 but less than 3, box of x will be 2. So, this would become like a x minus 2. Right? X is greater than or equal to 3, less than 4. This will be x minus 3. And so on and so forth. Right? So then, and similarly, when x is greater than or equal to minus 1 and less than 0, what would box x be? Minus 1. So this will become x plus 1, right? Plus 1, etc. Right? Now, start with this. When x is greater than or equal to 0, less than 1. When x is greater than or equal to 0, less than 1. Fractional part of x goes as the line y equal to x. Goes as the line y equal to x. This is the line y equal to x. When x comes closer and closer and closer to 1. When x comes closer and closer to 1, fractional part of x comes closer and closer to 1. As x comes closer and closer and closer to 1, fractional part of x comes closer and closer and closer to 1, right? The y's come closer and closer to 1. It's going as the line y equal to x, right? But the moment x becomes equal to 1, fractional part of x dips to 0. Whenever x becomes equal to 1, fractional part of x will become 0. There is an abruptness here. There is an abruptness seen here, right? So this is a point on the graph of the function, whereas this is a kink. This is not a point on the graph of the function, right? X comes closer and closer to 1. It's going as y equal to x in the interval 0 to 1. Y equal to x is a straight line passing through the origin, making an angle 45 degrees with the positive direction of the x-axis, right? So fractional part of x, which are the y's, are coming closer and closer and closer and closer to 1. They can be made as close to 1 as you like, but they will never become equal to 1. Why? Because in the event x becomes equal to 1, it suddenly dips to 0. Fractional part of x brings it down to ground state, right? Okay. When x is greater than or equal to 1 but less than 2. It goes as the line y equal to x minus 1. It goes as the line y equal to x minus 1. Yes or no? And y equal to x minus 1 has an x-intercept 1, right? At x equal to 1, y becomes 0. At x equal to 1, y becomes 0. And x and x minus 1 are parallel lines, right? So y equal to x minus 1 is actually parallel to y equal to x. This is the line y equal to x. Now this is the line y equal to x minus 1. This is the line y equal to x minus 1, which is obviously parallel to the line y equal to x at x equal to 2. So y equal to x minus 1, as x comes closer and closer and closer to 2, x minus 1 comes closer and closer and closer to 1. X minus 1 is coming closer and closer and closer to 1. The moment x becomes equal to 2, fractional part of x will dip to 0. Fractional part of x will dip to 0. So this is a point on the graph of the function, whereas this is not a point on the graph of the function. Yes or no? Are you all there with me? Similarly, when x is greater than or equal to 2, less than 3, it goes as the line y equal to x minus 2, which again is parallel to x. At x equal to 2, it's 0. And as x comes closer and closer to 3, x minus 2 will come closer and closer to 1. As x comes closer and closer to 3, x minus 2 will come closer and closer to 1. But the moment x becomes equal to 3, fractional part of x will dip to 0. Right? Fractional x dip to 0. So this is a point on the graph of the function, whereas this is a kink, not a point on the graph of the function. And so on and so forth. The graph will then continue to exhibit a trend like this. Three to 4, go this way, 4 to 5, go this way, and so on and so forth. Right? Now, when x is greater than or equal to minus 1 and less than 0, it goes as the line y equal to x plus 1. It goes as a line y equal to x plus 1, and at x equal to minus 1 it is 0. X equal to minus 1, it's 0. And then it goes parallel to this line y equal to x plus 1 is this line. As x comes closer and closer to 0, x plus 1 will come closer and closer to 1. As x comes closer and closer to 0, x plus 1 will come closer and closer to 1. But the moment x is 0, fractional part of x will dip to 0. Fractional part of x will dip to 0 and so on and so forth. And then, the same thing happens. So this is like y equal to x plus 2 and so on and so forth. This is the graph of y equal to fractional part of x. This is the graph of y equal to fractional part of x. Now I'm so sorry. This is x plus 1. I'm so sorry. This is y equal to x plus 1. This will be y equal to x plus 2. This will be y equal to x plus 3 and so on and so forth. Yeah. Now the thing to be noticed here is that whatever I see for x lying between 0 and 1, I see the same thing lying between 1 and 2. And then the same thing lying between 2 and 3. And then the same thing lying between 3 and 4 and 4 and 5. And minus 1 and 0 and minus 2 and minus 1 and so on and so forth. Which means, if I just knew the graph between 0 and 1, all that I need to do is copy paste, copy paste, copy paste, copy paste over the entire real number line and get the graph of y equal to fractional part of x. Also, noteworthy, which you could have seen even otherwise. If I said fractional part of 0.2, that will be 0.2. If I said fractional part of 1.2, it will be 0.2. If I said fractional part of 2.2, that will be 0.2, 3.2, 0.2 and so on and so forth. Yes or no? Can I not say that fractional part of x will be the same as fractional part of x plus 1? Can I say this? Graphically, fractional part of x is the same as fractional part of x plus 1. This will be the same as fractional part of x plus 2. Will be the same as fractional part of x plus 3. Will be the same as fractional part of x plus any integer I. Will be the same as fractional part of x plus any integer I. You increase this quantity by 1 unit, the fractional part will be the same. Instead of 0.2, if you had 1.2, the fractional part will still remain 0.2. Instead of 1.2, if you had 2.2, the fractional part will still remain 0.2. 3.2, fractional part will still remain 0.2 and so on and so forth, right? So, fractional part of x is the same as fractional part of x plus an integer. Got me? Same thing, dude. Because suppose I said fractional part of minus 0.2. Okay, tell me what would be the fractional part of minus 0.2? 0.8. Integer to the immediate left of minus 0.2 is minus 1. So its fractional part is 0.8. Fractional part is 0.8. Realize that this is minus 0.2. This is 0. This is minus 1. What is this distance? 0.8. Right? This is 0.8. And the distance from the nearest integer to the left is fractional part of x. So fractional part of minus 0.2 is actually 0.8. Okay. Now, subtract 1 from this. This will be minus 1.2. The integer to the immediate left of this would be minus 2. What would be fractional part of minus 1.2? Same, 0.8. Right? Fractional part of minus 1.2, that will also be 0.8. So, fractional part of minus 1.2, fractional part of minus 2.2, fractional part of minus 3.2, etc. All of that would be 0.8. Clear? So, same thing really. Graphically also, That's a easy to notice fact. The graph of y equal to fractional part of x was like this. Between 0 and 1, it went like this. Between 1 and 2, went like this. Alright. Now, these are two parallel lines. This is x, right? If you look at, now, if this distance is equal to this distance, see, from similar triangles, look at these two triangles. Look at these two triangles. This distance is x, suppose, and this is also x. Then what would this number be? This would be x plus 1. If this is x, and this is also x, then this point would be actually x plus 1. This point on the real number line would be x plus 1. Yes or no? And now, these two are congruent triangles. These two are congruent triangles. Realize that? Right angle, 45 degrees, 45 degrees, this length equal to this length. They are congruent triangles. So, do you realize that this length will be equal to this length? This length will be equal to this length, but what is this length? This length is fractional part of x. What is this length? Fractional part of x plus 1. All of these are fractional part of these corresponding numbers, the verticals. Right? So, if this is fractional part of x, this is fractional part of x plus 1 and they are equal. You see that they are equal. Right? So, fractional part of x is the same as fractional part of x plus 1 and will be the same as fractional part of x plus 2 in general, the fact that I mentioned. That means this function, fractional part of x, replicates its value at intervals of 1 unit. Replicates its value at intervals of 1 unit. Each time you increase x by 1 unit, the function, each time you increase x by 1 unit, see, this is increment in x by 1 unit, the function has replicated its value. The function has replicated its value. Clear? Sounds alright. What would be the fractional part of box of x? 0 for any x, because the output of box of x will be an integer and the fractional part of an integer will always be 0. Right? What would be box of fractional part of x? Because fractional part of x will be greater than or equal to 0, less than 1 for any real x. Right? So, box of fractional part of x will always be 0. Why? Because the quantity inside the box is fractional part of x, which will always be greater than or equal to 0 but less than 1. Right? So, box of a number lying between 0 and 1 will always be 0. So, fractional part of box of anything will be 0. Box of fractional part of anything will always be 0. Clear? Now, some more issues related to this function, box function. Suppose I have y equal to box of x plus I, where I is an integer, not necessarily integral part of x, I is any integer. Then realize that x is what? Its integer part ix plus its fractional part fx. Any number real x is like integer part, which is its box, fractional part, the number within curly braces, right? This will always be greater than or equal to 0, this will always be and less than 1, and this would always be an integer, right? Any number could be written like this. A number greater than or equal to 0 less than 1 plus an integer, right? Now, box of x plus I is like, write x as I plus ix, right? I plus ix plus fx. That means the integer part of this number, this is a number lying between 0 and 1. The integer part of this number would be I plus ix, yes or no? The integer part, the box of this number would be I plus ix. Yeah, I mean if I have box of 3 plus 0.2, then what would its box be? 3. Because this is 3 integer, to the immediate left of this number would be 3. Right? So box of I plus f will always be I, where f is a number lying between 0 and 1, will always be I. So this is I in this case is I plus ix plus fx. The integer part of this number would be I plus ix, I plus ix. Where what is ix? Ix is box of x. Ix is box of x. Alright, I'm sorry. So, the integer part of an integer plus a fraction would be the integer. So, that's going to be I plus ix. Where what is ix? Ix is actually the box of x. Ix is actually the box of x. So, this is like box of x plus I, which is a very important property. This is a very important property. Box of x plus I would be box of x plus I, would be box of x plus I. So, if I have any real number x, then x minus 3, box of x minus 3 is going to be box of x minus 3. Is going to be box of x minus 3. Right? Box of x plus 4 is going to be box of x plus 4. For any real x, box of x plus I is going to be box of x plus if I is an integer, if I is an integer. Can I wipe this off now? So this is a useful property. Box of x plus an integer would be box of x plus the integer. Now, look at y equal to box x plus box minus x, where x is any real number, box x plus box of minus x. Now, two possibilities arise when x is an integer, when x is not an integer. When x is an integer, then box of x will be equal to x, and when x is an integer, minus x is also an integer. Then its box would again be minus x, so it will be 0. Whenever x is an integer, box of x plus box of minus x will be 0, whenever x is an integer. When x is not an integer, then x could be written as an integer plus a fraction. Then x could be written as an integer plus a fraction, where f is greater than or equal to 0 but less than 1. When x is not an integer, x could be written as integer plus a fraction, where f is greater than or equal to 0 but less than 1, right? In which case, box of x plus box of minus x will be box of I plus f plus minus I minus f Yes or no? Right? Now, box of I plus f is going to be I. The integer part of this is I. Because this is a number lying between 0 and 1, then its integer part will always be I. Now, this will not be minus I. Because minus f is not a number lying between 0 and 1. Minus f is not a number lying between 0 and 1. What you might then want to do is, you might want to write this as minus I minus 1 plus 1 minus f. You might want to write this as minus I minus 1 plus 1 minus f. Right? Okay. Now, f is a number lying between 0 and 1. So, 1 minus f will also be a number lying between 0 and 1. If f is a number lying between 0 and 1, then 1 minus f will also lie between 0 and 1. Yes or no? If f is 0.8, then 1 minus 0.8, 0.2 will also lie between 0 and 1, right? If f lies between 0 and 1, 1 minus f will also lie between 0 and 1. So now, for this number inside, what's the fractional part? 1 minus f. Fractional part will always be a number lying between 0 and 1. So in this case, minus f doesn't lie between 0 and 1. But 1 minus f lies between 0 and 1. So 1 minus f is the fractional part of this number. 1 minus f is the fractional part of this number. What's the integer part of this number? Minus I minus 1. That's the integer part of this number. So then, this is like I plus minus I minus 1. Minus I minus 1. That's the integer part of this number. Right? And that's equal to minus 1. That's equal to minus 1. I mean, if x say minus 2.1 plus 2.1, what would be box of 2.1? 2. Now, what would be box of minus 2.1? Minus 3. Minus 3. So, box of x plus box of minus x will be minus 1 when x is not an integer. Whereas when x is an integer, box of x plus box of minus x will be 0. Again, we are going to use this time and again. Clear? Are you all certain about everything that I've said? Few of the properties, I'll just make a mention of those properties for the time being. For box function, number 1, let's say whenever n is an integer, box of box x by n will be box of x by n. This is one property. You just take notice of this. Box of box x by n is box of x by n. A lot more important, however, is the following property. This property is used only sometimes, but a lot more important property is the following, which is used time and again. And this property, whenever n is a natural number, x plus 1 by n, x plus 2 by n, x plus n minus 1 by n, that's going to be box of nx. This is an extremely important property. Box of x plus box of x plus 1 by n, box of x plus 2 by n. For n to be a natural number is going to be box of nx, right? And another not that commonly used property, box of x plus y can have just two values. It will either be box of x plus box of y, or it will be box of x plus box of y plus 1. Box of x plus y will either be box of x plus box of y, or it's going to be box of x plus box of y plus 1. This is not that commonly used, but this property of the amongst the three, this is the most commonly used property. Box of x plus this is box of nx. Make sense so far? Right? Okay, just take a couple of minutes off and then we. So, we learned two more functions today, the box function and the fractional part, right? Some of the properties related to that. In fact, these are quite favorite in as far as exams are concerned. People like to put a box and curly braces everywhere and give you some sophistication in problem solving. Now, one very important thing which we're going to encounter in functions, and that's called periodicity of functions. Periodic functions. Now, if a function has the following property, that means if f of x plus t is fx, for all x belonging to the domain of the function, for all x belonging to the domain of the function, if I can find a number t greater than 0, if I can find a number t greater than 0, then the function is said to be periodic. Function is said to be periodic. That means, now henceforth, this is like, f is like a rule which can act on a number to give you an output. What this means is, this is a rule acting on this number to give me an output. The same rule, when acting on this number, will also give me the same output. Now, the number on which f acts, the rule acts, I would often refer to as the argument of the function. I would refer to that as the argument of the function. This rule is acting on x. I would call x the argument. In this case, the argument is x plus t. So, if a function is periodic, what it really means is that you increase the argument by an amount t, the function will replicate its value. If you increase the argument, this x, this argument, when increased by an amount t, will cause the function to replicate its value. So then, the rule f, when acting on this, is the same as the rule f acting on this plus t. If t is the periodicity of the function, t is the periodicity of the function, then the rule acting on this is the same as the rule acting on this plus t. That means, if the argument now is increased by t, it will become x plus 2t. Again increased by t, it will become like a f of x plus 3t. Again increase it by t, x plus 4t, and in general, it will be x plus some n times t. N is an integer. So if a function is periodic, what it means is that we can find a certain number t. We can find a certain number t such that on increasing the argument by an amount t, the function replicates its value. That's what is meant by periodicity of the function. Now, you can say that t is the period of the function. You could also say that 2t is the period because you increase by an amount 2t. f of x plus 2t is the same as f of x plus 4t. Or f of x is the same as f of x plus 2t for all x belonging to the domain of the function. That means this suggests that 2t is the periodicity of the function. F of x is f of x plus 3t. This suggests that 3t is the periodicity of the function. Yes, they are all periods of the function. G, 2t, 3t, etc. They are all periods of the function. The function is periodic. You increase the amount by argument by an amount t, or by an amount 2t, or by an amount 3t, or by an amount 4t. The function will replicate its value. Right? They are all periods of the function, but the smallest positive member of this set is the fundamental period. These are all periods of the function. These are all periods of the function, t, 2t, etc. They are all periods of the function. But the smallest positive member of this set, the smallest positive member of this set is called the fundamental period. Called the fundamental period. That's the fundamental period, right? Now, suppose f of x is a function with fundamental period t. F of x is a function with fundamental period t, let's say. That means you increase this argument by an amount t, the function will replicate its value. F of x is the same as f of x plus t. Right? Now, suppose you have a function f, the same rule f, now acting on, let's say, some ax plus b. Let's say a is positive. Let's say a is a positive number. Right? The new argument is ax plus b. The new argument is ax plus b. Right? So f acting on this will produce the same output as f acting on this plus t. F, see, if I say the period of this function is t, what it means is f acting on a certain number is the same as f acting on that number plus t. Right? Each time you increase the argument by an amount t, the function will replicate its value. So this is the same as f ax plus b plus t. F of ax plus b plus t. That's true, right? I'm claiming that fx is a function with fundamental period t. With fundamental period t. Clear? Now, when I talk of the period, what it really means is the smallest amount by which x must be increased. The smallest amount by which you must increase x so that the function replicates its value. The smallest amount by which you must increase x so that the function replicates its value. Now in this case, this you realize, the rule acting on this is the same as the rule acting on this plus t, giving you the same output. Now this can be written as f of a into x plus t by a plus b. A into x plus t by a plus, which means that if I look at a function phi x, which is like ax plus b. Suppose I imagine a function phi x which is f of ax plus b. Then if this is phi at x, do you realize that this is phi at x plus t by a? If this is phi x, then this is the same as this except that x has been replaced by x plus t by a. Yes or no? If phi x is this, then what would be phi of x plus t by a? It means replacing x by x plus t by a. Plus b. Right? Which means, do you realize that phi x then is like a phi of x plus t by a? Right? That means, is phi x periodic? What is its periodicity? T by a. T by a is its periodicity. T by a is its fundamental period. So if fx has a fundamental period t, then f of ax plus b, which is phi x, f of ax plus b, which is phi x, is also periodic, and the fundamental period of phi x will be, that is fundamental period of f of ax plus b will be t by a if a is greater than 0. You know what I'm saying? Please understand this again. F of x is f of, that means the rule acting on a certain number is the same as the rule acting on the number plus t. I know f has a fundamental period capital T. Now instead of f of x, I have a new function which is f of ax plus b. F of ax plus b. And then attempting to find the periodicity of f. Periodicity of f of ax plus b. Okay. What we've already figured out is that f is periodic with fundamental period t. That means f acting on this is the same as f acting on this plus t. This plus t, right? Which is the same as f of a into x plus t by a plus b. And now if this is phi x, ax plus b, whose periodicity we set out to find. If this is phi x, then this is phi at x plus t by a. This is phi, if this is phi x, then this is the same as this, except that x has been replaced by x plus t by a. So if this is phi x, this is phi at x plus t by a. That means phi x is phi of x plus t by a. So what's the periodicity of phi x? T by a. That means if fx has a fundamental period t, f of ax plus b will have a period t by a. That's the rule. So if fx has a fundamental period t, then f of ax plus b will have a fundamental period t by a. If a is greater than 0. If a is greater than 0. Right? And if a is less than 0, then its fundamental period would be t by mod a. T by mod a. If a is less than 0, its fundamental period would be t by mod a. So in general, if fx has a period t, then f of ax plus b would have a fundamental period t by mod a. Clear? That's a very important rule. If fx has a period t, then f of ax plus b would have a fundamental period t by mod a. Clear? Now, do you realize that the function that we just encountered a little while ago, y equal to fx equals fractional part of x. Y equal to fx equals fractional part of x. This is periodic. And it has fundamental period 1. Do you realize that fractional part of x is the same as fractional part of x plus 1 for all real x? Right? That means f of x is the same as f of x plus 1. We just saw this graphically a little while ago. So, what's the fundamental period of f? 1. T equal to 1 is the fundamental period of f. T equal to 1 is the fundamental. That means fractional part of x is periodic and has periodicity equal to 1. Now in contrast, suppose I had a function f of 3x plus 4. What would its period be? This is f of x, this is f of ax plus b. Do you realize that? So its periodicity would be 1 by 3. If fx has a period 1, then f of ax plus b, this is f of 3x plus 4. Do you realize that? This is f of 3x plus 4. If that's fx, then this is f of 3x plus 4. Right? And the period of this is going to be 1 by 3. Right? What would be the periodicity of 1/3 x plus 4? 3. 1 by 3. The periodicity of this would be 3. What would be the periodicity of minus 2x plus 1? Periodicity will t by mod a, 1 by mod of minus 2. That is 2. Periodicity of this would be 2. So in general, if fx has periodicity t, f of ax plus b will have periodicity t by mod a. T by mod a. Clear? Y equal to sin x. Y equal to fx equal to sin x. Realize that this, the graph of y equal to fx equal to sin x is like this. And so on and so forth. This is the graph of y equal to fx equal to sin x. Now notice that, observe the graph in the interval 0 to 2 pi. Observe the graph in the interval 0 to 2 pi. Right? And essentially all these values are replicated. You can copy and paste. Whatever you see of the graph in the interval 0 to 2 pi, the same graph gets replicated again and again and again and again. Do you realize that? That means f of x is the same as f of x plus 2 pi for all real x. Sin of x is the same as sin of x plus 2 pi for all real x. Right? So can I say that 2 pi is the fundamental period of sin x? 2 pi is the fundamental period of sin x. Clear? See? So what really you can do is, if a graph is drawn over a length equal to one period. See, this is a length over one period. 0 to 2 pi is one full period. Then the same graph gets replicated again and again. You can copy and paste to get the graph of the function over the entire domain of description, right? So 2 pi is the period of sin x. 2 pi is the period of sin x. Okay. Now if I had a function which is like sine of 5x plus 11, what would be the periodicity of this? 2 pi by 5. This was f of x, this is f of ax plus b. The periodicity of this is going to be 2 pi by 5. What would be the periodicity of sine x by 5 plus 7? 2 pi by 1 by 5. 2 pi by 8. That is 10 pi. What would be the periodicity of sine of minus 1/3 x plus 8? 2 pi by 1/3. That is 6 pi is the periodicity of this. Yes or no? What would be the periodicity of sine pi x plus 4? 2 pi by pi. 2 pi by pi. That is 2. Right? Did you get me right? Now, the functions sin x, cos x, sec x, cosec x all have periodicity equal to 2 pi. All have fundamental period equal to 2 pi. All have fundamental period equal to 2 pi. Now, the graph of y equal to sin x graph of y equal to sin x was like this, right? Now if I said the graph of y equal to sin square x, hey, all these numbers would get squared, right? All these numbers would get squared. Let's say between 0 and pi, it will still be positive, but these numbers would change, right? If there is a 0.1 here, it will become 0.1 squared and so on and so forth. All these numbers would change. And the numbers appearing here, this would be the same as here. This will also get rid. It will just come out. These numbers would become positive. Square of these numbers, and this portion will move up. That's sin squared x. This will be the graph of y equal to sin squared x. It will be all positive. Do you realize that this would be the graph of y equal to sin squared x? Y will always be positive and will lie between 0 and 1. It will never be negative, right? Squares of all the signs. And then do you realize that this is 0 pi, 2 pi, 3 pi, 4 pi, minus pi, minus 2 pi, etc. Now, the same graph that you draw between 0 and pi can be copied and pasted here to get the graph between pi and 2 pi. Copy and paste this to get pi and 2 pi and 3 pi and 3 pi and 4 pi. Do you realize that all the values between 0 and pi get completely replicated between pi and 2 pi? So, if this is x, this would be like, this is x plus pi. This would be like a x plus pi. Do you then realize that at intervals of pi units, the value of sin squared x would get replicated. At intervals of pi units, sin squared x would get completely replicated. So then, would you fail to recognize that the period of this is now no longer 2 pi but is pi. Period of sin x is 2 pi, but the period of sin squared x would be pi. Fundamental period is going to be pi. Could have also said, well, sin squared x is half of 1 minus cos 2x. Sin squared x is half of 1 minus cos 2x. Now, I told you period of cos 2x is 2 pi. So, the period of cos 2x would be 2 pi by 2, that is pi. Okay. Now, the period of sin squared x will be the same as the period of cos 2x, right? Each time cos 2x repeats its value, sin squared x would repeat its value, right? Each time cos 2x repeats its value, sin squared x would also repeat its value, right? Cos 2x repeats its value each time x is increased by pi units. Why? Because the fundamental period of cos 2x is going to be pi. Cos x has a period 2 pi. Cos 2x will have a period 2 pi by 2, which is what I meant, pi, right? So the period of sin squared x is the same as period of cos 2x, which is pi. Clear? So the period of sin squared x would be pi. Similarly, if you had like a cos squared x is like a half of 1 plus cos 2x. Cos squared x is half of 1 plus cos 2x. Now, period of cos squared x will be the same as the period of cos 2x. Each time this repeats its value, cos squared x will also repeat its value. So, what's the period of cos 2x? Pi. So, what's the period of cos squared x? Pi. Period of cos squared x will be pi. Similarly, period of sec squared x will be pi, period of cosec squared x will be pi. So, period of sin squared x, period of cos squared x, period of sec squared x, period of cosec squared x will all be pi, Whereas period of sin x, cos x, sec x, cos x will be 2 pi, period of sin squared x, cos squared x, sec squared x, cosec squared x, that will all be. Now, I'll make a general remark which we will use in problem solving. The general remark is that sin x to the power n, cos x to the power n, sec x to the power n, and cosec x to the power n. When n is odd, the fundamental period of all these functions would be 2 pi. When n is even, the fundamental period will be pi. Remember this result. Whenever n is odd, the fundamental period of all of this would be pi, and whenever n is even, the fundamental period would be pi. Like we saw for n equal to 2, the fundamental period of this became pi, right? Whenever n is odd, for example, when n was 1, the fundamental period of this was 2 pi, right? So this is one result that you may want to remember. For n even and n odd, for these trigonometric functions, sine, cosine, sec and cosec, this would be the fundamental period, right? So, what would be the fundamental period of sine cube 3x? Fundamental period of sine cubed x would be 2 pi. So, fundamental period of sine cube 3x would be 2 pi by 3. 2 pi by would be the fundamental period. Yeah? Right? Tan x and cot x. See, tan x is the same as tan of x plus pi for all real x. The smallest increase in x that will cause the tangent function to replicate its value is pi, right? Similarly, cot x is the same as cot x plus pi. The fundamental period of tan x and cot x is therefore pi. The fundamental period of tan x and cot x is pi. Now, as far as tan x and cot x are concerned, again a remark that I want to make, and you might want to explore this at home, that tan x to the power n and cot x to the power n will always have a period equal to pi for n even as well as odd. For n even as well as odd, tan x and cot x will always have a period equal to pi, for n even as well as n odd. Remember this result. That means period of tan squared x will be pi. Period of cot cubed x will be pi. Whereas the period of cot cube 5x will be by 5, right? Would be pi by 5. Period means the smallest amount by which you must increase x so that the function replicates its value. That's the fundamental period, right? So in this case, the smallest amount by which you must increase x so that the function replicates its value is pi by 5. That means if you replace x by x plus pi by 5, the cot cube 5x will repeat its value. Clear? Hey, if somebody offers, I hope you're all there with me on this, you've understood everything that I've said, right? Somebody offers the graph of y equal to fx to you. Okay, let's say between x1 and x2. I draw the graph of y equal to fx. This is the graph of y equal to fx between x1 and x2. And I want to draw the graph of, say, let's say this is A, this is B. And I want to draw the graph of y equal to mod fx. I want to draw the graph of y equal to mod fx. Then, from the definition of the mod function, mod of something will be equal to something when that something is greater than or equal to 0. Mod of something will be equal to something when that something is greater than or equal to 0. Else, it will be negative of that something. When the quantity inside the modulus, is less than 0, the modulus would be negative of that. Yes or no? Right? So then, whenever fx is greater than or equal to 0, mod of fx is the same as fx. That means, whenever fx is non-negative, the graph of y equal to mod fx and graph of y equal to fx would be the same, right? When is fx greater than or equal to 0? x1 to a and b to x2, right? Fx is greater than or equal to 0 in this interval and in this interval. Yes or no? In the interval x1 to a and in the interval b to x2, right? That means in this interval, the graph of fx and mod fx will be the same. In the interval x1 to a, fx is greater than or equal to 0. So fx and mod fx would have the same looks. And in the interval b to x2, this is fx. Again, fx is greater than or equal to 0 in this interval. So the graph of y equal to fx and graph of y equal to mod of fx will be the same. Right? In the interval b to x2, this graph fx and graph of y equal to mod of fx would be the same. Clear? However, when fx is less than 0, see, this is the case where fx is less than 0. In the interval a to b, fx is less than 0. Then the graph of fx, the graph of mod of fx would be negative of the graph of fx. The graph of mod fx would be negative of the graph of fx. The graph of fx is like this. So negative of fx would be a graph like this. Negative of fx, if this is fx, then negative of fx would be this. Yes or no? Are you all there with me? Clear? So each time you have the graph of y equal to fx and you propose drawing the graph of y equal to mod f of x, just write down. Given the graph of y equal to fx, if one has to draw the graph of y equal to mod of fx, given the graph of y equal to fx, if one has to draw the graph of y equal to mod of fx, Number one, in an interval in which fx is non-negative, the graph of fx and mod fx would be identical. The graph of fx and mod fx, graph of y equal to fx and y equal to mod of fx would be identical. Number two, in an interval in which fx is negative, the graph of y equal to mod of fx, can be obtained by reflecting that portion of the graph of y equal to fx about the x-axis, about the x-axis. What I meant was, this was the graph of y equal to fx. If I have to draw the graph of y equal to mod of fx, well, there are intervals in which fx is positive, there are intervals in which fx is negative. In the interval in which fx is positive, fx and mod fx would have the same y, right? So in that interval, the same portion gets replicated, right? See, in the interval x1 to a, fx is positive. In the interval b to x2, fx is non-negative. So in these two intervals, the graph of fx and mod of fx would be identical. However, in the interval a to b, where fx is negative, the graph of mod of fx, see, the graph of mod of fx would always have a non-negative output. So then, negative of these numbers would be mod of fx, right? If this is fx, then negative of this number would be mod of fx, and negative of this number is like a mirror image about the x-axis. So reflect this portion about the x-axis, reflect all these points about the x-axis to get the corresponding point. And when you do that, you get this. This would then be the graph of y equal to mod of fx. So wherever fx is negative, reflect that portion about the x-axis to get the complete trace of y equal to mod of fx. Yes or no? Don't tinker with the portions which are already positive or non-negative. However, portions that are negative, reflect those portions about the x-axis and you will get the graph of y equal to mod of fx. Yes or no? Say, y equal to sin x. This is the graph of y equal to sin x, right? I want to draw the graph of y equal to mod of sin x. Okay. Now in the interval 0 to pi, sin x is non-negative. So the same portion will get replicated in the interval 0 to pi. Right? In the interval pi to 2 pi, sin x is negative. So mod of sin x would be negative of these numbers. Negative of these numbers would be these numbers. Right? Negative of these numbers would be these numbers. So mod of sin x . 0 to pi and pi to 2 pi. This is the graph of y equal to mod of sin x. This is the graph of y equal to sin x. This is the graph of y equal to mod of sin x. Clear? So we'll have to retain these positive portions. Wherever sin x becomes negative, reflect those portions about the x-axis to get the graph of y equal to mod of sin x. Clear? So then, tell me, the periodicity of sin x is 2 pi. What would be the periodicity of mod of sin x? Pi. Right. So, mod of sin x has periodicity equal to pi. Sin x has periodicity 2 pi, whereas mod of sin x will have periodicity pi. Similarly, mod of cos x will also have periodicity pi. Periodicity pi. Mod of sec x will have periodicity pi. Mod of cosec x will have periodicity pi. Clear? In fact, if you recall, I told you root of x squared is mod x, right? Root of x squared is mod x. So, can I say mod sin x is actually root of sin squared x? Can I say this? Right? Which is root half of 1 minus cos 2x. So, mod sin x would repeat its value each time cos 2x repeats its value. So, the periodicity of mod sin x is the same as the periodicity of cos 2x. But what's the periodicity of cos 2x? 2 pi by 2, which is another way of looking at it. Got me? And similarly for mod cos x is actually root cos squared x, which is half of 1 plus cos 2x, and will inherit periodicity from cos 2x. Periodicity of cos 2x is 5. So same as mod cos x. Same for sec x and cosec x. Clear? Now, so far so good, right? You understand all these ideas. Suppose you have a number of functions. One thing, if fx has a period t, then a constant times fx will have the same period. That's not going to, this function will have the same period as the period of fx, right? Now, suppose we have number of functions a1 f1x plus a2 f2x plus a3 f3x plus an fnx. Okay. And let's say this is a function fx. This is a function fx. And say f1x has a fundamental period t1. f2x has a fundamental period t2. f3x has a fundamental period t3. fnx has a fundamental period tn. Right? Then the periodicity of fx could be fx could be, need not necessarily be, could be LCM of T1, T2, T3, Tn. Could be the LCM of this number. provided the LCM exists. If the LCM of these numbers doesn't even exist, then fx is not periodic, right? But even when the LCM exists, this may or may not be the fundamental period of fx. Sorry? If the LCM doesn't exist, then of course fx doesn't have a period. But in the event LCM does exist, even then the period of the function need not be LCM of these numbers. It could be half of the LCM. It could be half of the LCM of T1, T2, T3, Tn. I'll demonstrate this. If the LCM exists, the period could be LCM of these numbers, or it could be half the LCM of these numbers. Sorry? I'll give me a moment here. I'm still in the process of building this entire story for you. Give me a few moments, right? I will not leave it unattended. Okay. In fact, it may not even be this. It may not even be this. It could be this, or it could be this, or it may not even be this. One thing, let me take simple cases. Okay. Suppose I have a function sine 2x plus 4 plus 3 cos 5x plus 8. Okay. This is a function. What's the fundamental period of this? Pi. 2 pi by 2? Pi. What's the fundamental period of this? 2 pi by 5. Now, in this case, the LCM, the period of fx would indeed be LCM of pi and 2 pi by 5. The LCM exists in this case. The LCM of this is like, you can take pi common, it's going to be LCM of 1 and 2 by 5. LCM of 1 and 2 by 5. Now LCM of two fractions is, what is the LCM of two fractions? Look, go back to class 4. Learn your LCM SCF, right? LCM of two freaking fractions. LCM of numerators divided by HCF of denominators. LCM of a number of fractions. LCM of a number of fractions is going to be LCM of numerators divided by HCF of denominators. That's the LCM of fractions. You never learned this in junior class. God bless you. It's going to be LCM of 1, 2 divided by HCF of 1, 5. LCM of fractions is LCM of numerators divided by HCF of denominators. Right? LCM of 1 and 2 is 2. ये तो पता है ना? HCF of 1 and 5 is? Somebody whispered 5. HCF of 1 and 5 is? 1, right? LCM of 1 and 2 is? 2, right? So it's going to be 2 by 5. Wow. 5 times 2. Not by 5, right? By 1. HCF of 1 and 5. Okay. So, in this case, it's alright. Right? Now, there could be a situation where the LCM does not even exist. I'll tell you when. In this case, the LCM exists and the periodicity of the function is really the LCM of the periods of this and this function. That's the LCM of this. The period of fx then is 2 pi, in this case. Clear? Suppose I had a function fx which is sine 3 pi x plus 1 cos 2x plus 5. What's the period of this? 2 by 3 is the period of this. Right? 2 pi by 3 pi. What's the period of this? 2 pi by 2, that is 5. Now, LCM of 2 by 3 and 5. What is it? Does not exist. LCM of a rational and an irrational number cannot be found. It does not exist. LCM of a rational and irrational number does not exist. Okay, LCM of 2 and root 2 is what? LCM of 2 and root 2 is? Yeah, and I'll tell you, preceding all this discussion, you would have been tempted to say that it is 2 root 2. Or somebody might simply say 2. Somebody might say 2 root 2, or somebody might say 2. Right? Why is this not the LCM of these two? Okay, why is this not the LCM of these two? Why is this not the LCM of these two? Because if this were the LCM of these two, then this by this should be an integer and this by this should also be an integer, isn't it? If LCM of A and B is C, then C by A should be an integer and C by B should also be an integer. So 2 by 2 is an integer, but is 2 by root 2 an integer? No. So this is junk. LCM of a rational and irrational number will never exist. So LCM of 2 and root 2 does not exist. So LCM of 2 by 3 and 5 does not exist. So fx has no period. fx is not periodic. fx is not periodic. Right? Again, I'll demonstrate a case where the LCM rule finds itself nude. What's the periodicity of sine squared x? Pi. What's the periodicity of cos squared x? Pi, right? Look at a function sine squared x plus cos squared x. This has periodicity pi. This has periodicity pi. What's the LCM of pi and pi? Pi, but is pi the periodicity of this? This is a constant function 1. Sine squared x plus cos squared x is 1. Yes or no? Sine squared x plus cos squared x is 1. It is periodic, but it has no period. Every constant function is periodic, alright, but you can't find a goddamn period for that function. Any number would be a period. I mean, suppose I have a function f of x equal to a constant k. Right? Then for any t f of x plus t will be k. But what is this t? You come up and say t is 0.01. He says it's 0.001. All are right, but no one is right. A constant function is periodic without any fundamental period. A constant function is periodic, yes. Let's say at the interval of 0.1 units, the function will repeat its value. That's right, but it will also repeat its value at the interval of 0.01 units. For every number that you quote, I'll quote a number smaller than that. So we will not converge to a number which will be the period of a constant function, yet it's periodic. Because for any t, f of x plus t will be equal to f of x will be equal to t. Clear? So, a constant function. So, this is a constant function It's not periodic, it's periodic, but doesn't have a period. But then, if you apply the LCM rule, it says the period is 5. Right? So the LCM rule has its limitations. The LCM rule has its limitations. Sometimes the LCM does not even exist. Whenever you encounter LCM of a rational and irrational number, the LCM will not exist. Sometimes even the LCM of two irrational numbers will not exist. I hope you're all there with me on this LCM HCF business, right? I'm sorry I got you started on all this without teaching you LCM HCF. I just assumed too much. It was a wrong beginning, in fact. Maybe in my Kabir Road class, I'll give them one class on LCM HCF before I teach them all this. Okay. See, interesting thing is the LCM of 2 pi by 3 and 5 pi by 4 will exist. They have the same irrational part. Pi can come out. Then it's going to be LCM of 2 by 3, 5 by 4, which is like 5 times LCM of the numerators divided by HCF of denominators. Right? This exists. Same irrational part. But if I had two irrational numbers, let's say LCM of pi and root 2. These are both irrational numbers, but their irrational parts are different. Then the LCM will not exist. The LCM of this will not exist. However, if you took the LCM of 3 root 2 and 5 root 2, then this LCM will exist because this root 2 will come out. It's going to be root 2 into LCM of 3 and 5. Right? That's what it could be. Root 2 into LCM of 3 and 5. So, first of all, LCM of two rational numbers will always exist. Be it integers or be it fractions. If it's fractions, then it's going to be LCM of numerators divided by HCF of denominators. LCM of irrational and rational number will never exist. LCM of two irrational numbers may or may not exist. For example, in this case it exists. In this case, the irrational parts are different. It does not exist. In this case, it exists because the same irrational part root 2 and it can come out. Do you all understand this? So, one thing, the LCM may not exist, then of course you don't talk of a periodicity. If it exists, it may or may not be the LCM. It may or may not be the LCM. Now, for example, I told you the periodicity of mod sin x is pi, right? The periodicity of mod sin x is pi. The periodicity of mod cos x is pi. Right? Figure this out. Look at a function fx which is like a mod sin x plus mod cos x. Now, the LCM of pi, pi, that might seem like being the period of this function. That might seem like being a period of this function, right? But it's a period, but it's not a fundamental period. Realize that if fx is mod sin x plus mod cos x, then f of x plus pi by 2 mod sin x plus pi by 2 plus mod cos x plus pi by 2. Now sin x plus pi by 2 is cos x and mod cos x. Cos x plus pi by 2 is minus sin x and mod of minus sin x is the same as mod of sin x. Hey, what transpires then is f of x is f of x plus pi by 2. What is the periodicity? Fundamental period is pi by 2. Pi is still a period but not a fundamental period. The fundamental period is pi by 2, which, like I said, is half of the LCM of T1, T2, Tn. I told you, right? It could be half the LCM of T1, T2. See, it's half the LCM of T1, T2. This is pi by 2. Right? No, what I'm saying. In general, then, let me quote the following for you. If I have A mod sin x plus B mod cos x, if I have a function fx which is A mod sin x plus B mod cos x, and if A is not equal to B, then the LCM is going to be pi, which would be pi, and this is going to be the period if A is not equal to B. If A is not equal to B, because see, in pi, if you replace x by x plus pi by 2, it will become A mod cos x plus B mod sin x, which is not the same as fx. Pi by 2 is not the period if A is not equal to B. If A is not equal to B, pi by 2 is not the period, right? But if A is equal to B, that's the case that we've explored, then the period is not going to be LCM of these two. It's going to be half of this, that is pi by 2. Half of the LCM of these two, that is pi by 2. If A is equal to B, that's the case we looked into. Then the periodicity is not going to be pi, but is going to be pi by 2, right? And the same thing for A mod tan x plus B mod cot x. If A is not equal to B, the periodicity will be pi, otherwise it will be pi by 2. If A is equal to B, it's going to be pi by 2. Whatever I have said of A mod sin x plus B mod cos x is true for A mod tan x plus B mod cot x, and is true for A mod sec x plus B mod cosec x. This will have a period pi if A is not equal to B, and will have a period pi by 2 if A is equal to B. Same with this. This will have a period pi when A is not equal to B, will have a period pi by 2 when A is equal to B. Just look into this once again. You understand all these ideas? Is there anyone who has a doubt on any one of these things? I hope by this time, at least one thing you know, how to find the LCM of A1 by B1, A2 by B2, AN by BN. How do you do that? Yeah. Now you see, become so vocal. LCM of numerators divided by HCF of denominators. And how do you find HCF of fractions? That's going to be HCF of numerators divided by LCM of denominators. HCF of fractions is going to be HCF of numerators divided by LCM of denominators, right? Not a problem, right? So now tell me, this is a function fx. What is its periodicity? This is a function fx. What is its periodicity? Happen, not a problem. Okay, what's the periodicity of this? What's the periodicity of this? 2 pi by pi, 2. The periodicity of tan cube x is pi. So the periodicity of tan cube mx would be pi by m. So this is going to be pi by 6 pi, that is 1 by 6. This is going to be LCM of 1, 2, 1 divided by HCF of 2, 1, 6. Right? What's the LCM of 1, 2, 1? What's the HCF of 2, 1, 6? 1. Thank God you know that. Okay. Suppose I had a function like this. What's the period of this? 1/3. What's the period of this? 2 pi by 3. What's the LCM of these two? God knows. Does not exist. Right? Does not exist. LCM of a rational and an irrational number does not exist. This is a rational number, this is irrational, it will not exist. Right? So you pretty much understand what a periodic function is. And I have one disclaimer here and an honest confession. There is no rule of finding the periodicity. Most of the time, barring these, let's say some fundamental function is given, either graphically or by inspection, you have to find the period. Alright? I mean, there is no formula that I can supply to you by means of which you can readily find the period. However, if you have constituent functions whose periods belong to some standard list, that's another issue. But if a period doesn't belong to a standard list, and then it may not be very direct sometimes to be able to find the period. You might have to do and deploy some inspection to be able to find the period of that function, right? So we'll have to play around a little bit, sometimes by inspection, sometimes by a graph, and sometimes look around and find out. Okay. Yet another way you could classify functions. So functions could be periodic, functions maybe non-periodic, right? Now, even before I spell out the other classification, let me also mention one more fact to you. If Gx is a periodic function, then f of Gx, will it be periodic? If Gx is periodic, will f of Gx be periodic? Okay, I will again not discuss this right now. I want you to think about this. F of Gx, when f is periodic, and think about f of Gx when G is periodic. I'll leave you with this thought on periodicity. Think about this, f of Gx and f of Gx for cases where f is periodic, case where G is periodic. Alright. We'll talk about this becomes an important point of discussion in periodicity, but even before I spell it out very discreetly in the class. I want you to let your imagination run loose on this and venture out. Now, another classification of functions is even and odd functions. A function is even when f of minus x is f of x. Then the function is said to be an even function. That means if you change the sign of the argument of the function maintains the same value. That's an even function. An odd function is when f of minus x is minus f of x. It's not like all functions have to be necessarily even or odd, right? Functions may be neither even nor odd, right? However, if I have a function which is neither even nor odd, in any case, any function could be written as a sum of an even and an odd function. I could write fx as f of x plus f of minus x by 2 plus f of x minus f of minus x by 2. Can I write fx like this? F of x plus f of minus x by 2 plus f of x plus minus f of minus x by 2, right? Okay. Now look at this phi x, which is f of x plus f of minus x by 2. Look at this phi x, which is f of x plus f of minus. Now, what is phi of minus x? F of minus x plus f of x by 2. Right? Do you then realize that phi of minus x is the same as phi of x? So, what do you think is phi? Even. Right? That means this function is an even function of x. So, this is an even function of x. Clear? In contrast, look at this. F of x minus f of minus, call it Lx. Lx is f of x minus f of minus x by 2. What is L of minus x? L of minus x is going to be f of minus x minus f of x by 2. That means replacing x by minus x throughout. F of minus x minus f of x by 2. Hey, but do you realize that this is minus Lx? This is minus Lx. Minus of this, right? So, Lx, L minus x is minus Lx means L must be an odd function. So, this is an odd function. So, every function could be written as a sum of an even and an odd function. Right? So, a function is either even or odd or neither. If it's neither, in any case, it could be written as even plus odd, right? Can I write this out? This is for today. Now, tomorrow, see, there is a original